Yeah.
Okay, let's get started with the next session. It's going to be Mike Frank from Stanford.
Hey, thanks very much for the invitation. This is already a really fun meeting. So many of you are computational scientists, so you're used to this, but for me, coming from a field that moves very slowly, it's a distinct surprise to be talking primarily about work that didn't exist half a year ago. So bear with me a little bit. Okay, so I'm going to be talking to you about bridging the data gap between human children and AI models. In particular, I'm curious about what recent progress in AI, NLP, computer vision can tell us about the nature of the human mind. The pace of progress has been astonishing, but one notable observation for anybody who's watching the field is how much of that progress relies on huge amounts of data. And so that's a really interesting issue to look into, the question of the sample efficiency of human children versus models. Here's my son Jonah and two of his buddies. He's 5, buddies are 5 and 7. They've just been taught the game Candyland. Similar to recent developments in AI, they're producing language, they're categorizing objects, they're doing some zero-shot learning. But the scale of learning that they're doing is different relative to the amount of language data they have access to, at least. So here I'm quantifying it just for language tokens or words here. So age is on the X, the order of magnitude of language input is on the Y. We don't have fabulous numbers for kids, but we can give good order of magnitude upper and lower bounds. So an upper bound that I frequently use is about 1 million words a month. So my 5-year-old heard maybe upper bound of 60 million words. And once he starts to read, you'll see this little uptick. Lower bound is about an order of magnitude lower than that, and it increases a little bit due to reading. Okay, you get zero-shot learning in GPT-3 around 500 billion words. Chinchilla is 1 trillion. GPT-4o, by some reports, is like 15 trillion or 16 trillion or something like this. So there is a very big data gap, depending on exactly where you compare these curves. Is it 3 orders of magnitude or up to 6 orders of magnitude in difference between the amount of language data that's required for a particular phenomenon to emerge in humans versus models? All right, so how could we explain this gap between human scale intelligence and LLM scale intelligence? Let's look to the cognitive science literature for a little bit of guidance. We have nativist theories, which focus on children's innate endowment, the evolutionary pre-training that allows them to learn quickly, perhaps because of their innate concepts of agents, events, number, physical properties of objects, and so forth. Constructivist arguments, in contrast, focus on the active and social nature of kids' learning, the way that their world is curricularized for them by the people around them, and the ways that they experiment on causally and learn from the world through their action. A third strand of thought focuses primarily on the multimodal grounding that children get, that their experience isn't simply through language, but that language is accompanied by a rich stream of sensory information, both visual and haptic and somatosensory and so forth. Finally, you might dismiss this picture and say, well, that gap is apparent rather than real because there are true evaluation issues here. The evaluation is actually everything. We are interested in multilingual question answering from GPT-4o, and we're interested in just barely being able to hang on in a kindergarten classroom from the 5-year-old. So maybe some aspects of this are really apparent rather than real. But I think there's a strategy that we can take to try to figure this out. And the basics of the strategy is that we take our algorithm of choice, we train it on children's training data, and we evaluate it on children's learning outcomes. And then we can make contrasts between that algorithm and others, say algorithms that have more pre-training or more innate conceptual biases or more ability to act in the world and get a reinforcement signal or something like this. Basically, the idea here is to use AI models, whether they're LLMs or other models, as cognitive models. So just to be clear about what I mean by this, the idea is that we've got a system that we're interested in as scientists, and this talk is purely really mostly focused on the idea of using AI models as a scientific tool to help us understand humans. So here's our target system, which is humans. They get some input, they've got some target behaviors. The is modeled by relation here is basically the idea that we are using another artifact in place of the human learner, one for which we can make more systematic causal interventions, sometimes interventions that we can't do on humans. We can do controlled rearing, for example, where we intervene on the input data and measure the effects on behavior. We can do various varieties of probing, where we investigate the causal dependencies between the internal states of the model and the observed behavior. Again, not something that's easy to do with humans. And then, of course, we can do behavioral evaluation, where we measure the behavior under different experimental conditions. And that we can do with both systems for the most part, although it can be cheaper with the models. Okay, so just to do a brief soapbox moment here, this isn't really a strategy that we can use with, for example, GPT-4o. We can't retrain the model. We don't know what the data are. We can't examine the representations or intervene on them. All we can do is the same stuff we can do with the humans. Depending on API pricing, it might be cheaper or more expensive. Okay, this is actually quite I think a very interesting paper using cognitive psychology to understand GPT-3, but I'd just like to point out that they're using only cognitive psychology and not neuroscience and development and so forth. And so to do cognitive modeling would be great to be able to bring to bear some of these other tools. All right, so I gave you a little bit of an intuitive idea of what I meant by a data gap and how this cognitive modeling strategy might help us understand it. Let's get just a tiny bit more precise. So for a specific task, for example, learning the grammar of a natural language, or visual categorization, or few-shot learning, we might define some axes. Ideally, the vertical performance axis is a human-compatible metric of some sort, and the horizontal axis is the amount of human data. And then there's some kind of age-level performance. Just for simplicity, we'll choose whether it's a 5-year-old that we want to match or a 21-year-old at Berkeley or something like this. And then we can figure out the data quantity at that particular age and plot model performance as a function of data quantity, and that gives us a data gap. So this is the kind of picture that I would like to be able to make to really truly understand whether an algorithm is in fact less sample efficient on a particular problem for a particular evaluation than humans are. I'm not going to get there quite today. I'll show you one of these pictures at least, but this is definitely the goal. So my lab builds open data resources. That's more or less what we do. We are a developmental psychology lab that tries to create resources both for understanding scientific domain questions about human development and also for enabling this kind of translational cognitive modeling work. So when I say we want to bridge the data gap, that's what I mean. We want to create the resources that allow us to understand this question and evaluate it. So we create resources around measuring kids' language input, around their language processing. So these are data aggregation from many different labs, and around their language outcomes. And basically the plan of the talk today is train on kids' data, evaluate on kids' outcomes, and I'll try to get you part of the way there. Okay, so part 1 is developmental training data, and part 2 is developmental evaluation. All right, so some first prerequisites. You might think, well, part of the difference here between GPT-style models or other language models and human kids is that models get internet data and kids get this wonderful curricularized input from their parents, and maybe that input is really awesome and that's what makes the difference. That's not true, unfortunately. I wanted it to be true, but it's not. So here's some simple pre-training experiments that Stephen Feng and Noah and I did. We trained GPT-2 on English language kid input from the Child Language Data Exchange system. So that's most of the extant public transcripts of kids talking and being talked to by their caregivers. We also created a matched corpus called Tiny Dialogues, which was inspired by Tiny Stories. This is like the maximally sanitized and curricularized version of Childess, where GPT-4 is pretending to be parents and kids talking. And so you get these kind of saccharine, asinine dialogues between the two of them, but that provide very heavily curricularized data where we've determined the vocabulary that's being used and calibrated prompts that provide developmentally appropriate 2-year-old and 5-year-old and 10-year-old dialogues. And then we also used this kind of generic training mixture that Baby LM put together, which includes Wikipedia, transcripts, books, again, size matched. And we evaluated on a syntax benchmark called Zorro and word similarity benchmark that folks have been using, basically looking at conceptual distances and comparing those to human conceptual distances. And the top line result is that child-directed speech was less useful. Tiny dialogues made up part of that gap, and baby LM was actually the most useful. We also hoped that curricularization here was really important, and that the developmental ordering was going to be really critical in childless. That wasn't true either. Random ordering is actually better than developmental curricularization here. Go ahead. Oh yeah. Well, so that, we'll get there. This is I'm the data person. This is hard, right? What grounding? Yeah, we don't have the child's experience for childless. Okay, but that's what we do. So probably about 10 plus years ago, we started doing these head-mounted camera experiments. So we collected this data set called SACAM, which is 3 kids, about 470 hours, 2 hours a week. These families were recording basically from when their kid was old enough to wear the camera on their head to when they turned about 2.5 and stopped having it. This is a relatively low quality data set, 640 by 480. The audio is not great. That's because we were buying these kind of low cost, low weight cameras, which were available at the time. The only people who wanted to do this experiment were developmental psychologists. So we got 3 kids of developmental psychologists. This is really not that fun. I was supposed to be a participant in the study and I declined after a week or so. It's a true story. Okay, but an important part about this data set, which is not true of other multimodal grounding of kids' experience, is that this data set is shared openly through databrary.org. That's a specific video sharing site for developmental videos. It's accessible to any researcher at a not-for-profit institution through an institutional agreement. If you're interested in getting data access here and are having trouble, please talk to me. This is a balance between the sensitivity of the videos, which include day-to-day activities, not just kind of play on the floor, but also diaper changes, bathroom, breastfeeding. So really fairly sensitive stuff, and the need for openness and data sharing. But the intent is for this to be available to any researcher who wants access. Our work builds on the shoulders of many people who pioneered this headcam method, including Linda Smith, Chen Yu, Karen Adolph, and others, Dick Aslan. And you see some of the insights that they had in their data as well, that the child's view is quite different than an adult's view. Notably, objects are much closer because kids have little dinosaur arms. So in our first work on this is led by Bria Long, who's a persistent protagonist in this talk. Bria was interested in answering a developmental psychology question, which is what kind of social information do kids have access to? What is the way in which people curricularize kids' visual experience? So we used, at the time, state-of-the-art pose detection. This was open pose. So we found better detections than kind of pure off-the-shelf, non-pose related detection benchmarks, but still really quite bad, even by the standards of then. Sort of lower recall, a bit higher precision for faces and hands. But something jumped out very consistently, which is that hands were almost always more accessible than faces, and this converges with a bunch of other findings in this work, where young kids have the world imposed on them by caregivers with hands. People put stuff down in front of them or manipulate things for them, and that's a really important piece of social input, at least for kids in these kinds of contexts. On the other hand, these data really didn't give us much traction on understanding supervised category learning. The videos were too low resolution, and so we got pretty bad segmentations. The view angle obscured what kids were interacting with. And further, something that's actually important about these data is that the distributions of objects in kids' homes are very long-tailed. So they mostly don't just see books in general, like ImageNet. They see this book, or this table, or this spoon. So we did very, very poorly in this kind of object work. The next step, though, was to try to actually understand whether these were good learning input. And this gets at the question. So here we were looking unimodal first, and we asked whether we could train unsupervised contrastive learning algorithms, things like SimClear and its relatives, on these SACAM data. And this is the work of Changshu Shuang, supervised by Dan Yeamans. So they ran these algorithms on SACAM videos and then asked about what the resulting representations looked like. And one measure here is to compare these representations with neural representations. Here, these are from Macaque IT, recordings, but there are other brain-inspired benchmarks that can be used. I would say this is a kind of glass half full, glass half empty. The unsupervised methods actually did pretty decently well on SACAM data, but they didn't do as well as those methods run on ImageNet or the supervised baseline. So Changshu and Dan came to me and said, you said this was a hard experiment to do, and it was kind of annoying, and it was a lot of data, but actually it's not very much data, and we'd like you to do a harder experiment. So that was fun. So that kicked off the BabyView project, which Bria has led over the past 3 years. We partnered with a design firm in San Francisco, Daylight Design, to develop a new lightweight camera based on the GoPro Hero Bones, which is a drone model of a GoPro. These are easy to build and easy to deploy. It takes about 10 minutes to build one in our lab now. And it's also got inertial motion units, IMUs, so that we can actually get a self-motion signal and use that as a signal to parse the video. We now build bouquets of baby views and send them out to families around California and around the US. And we are aiming for, by the end of next year, a data set that's closer to a single child year of video, which is about 4,000 hours. So that would be around the size of Ego 4D, which is the current benchmark egocentric adult video, or video from adults data set. So about 10x what we have now. We're not there yet. We have about 500 hours, so we can match SACAM here. So here's just an example of this type of data. So you can see this is actually one of Bria's kids doing a little puzzle here. So an important thing that you'll notice is that the field of view is much, much larger. We're actually using portrait rather than landscape to match the vertical field of view of a human child, which is much more closer to about 100 degrees. Let's see if this will okay. So because of the sensitive nature of these data, once we freeze the data set, which we've done, the first release becomes available 6 months after that. That's for an embargo for parents and families to claw back data that they don't want in the data set. And we have a variety of families involved, just kind of about 25 families that are currently contributing. Some have contributed actually over 60 longitudinal hours of data. And we just recruited another 15 families. So we're hoping for this large data set to accumulate over the next year and a half or so.
Found ya!
Kids don't just learn at home, they also learn in the classroom.
Do you want to be a real butter? I shall help! Do you want to be a real butter? No? Do you want to be a real butter?
Okay, so this is video from the on-campus nursery school at Stanford, where we have an entire classroom that Bobby Sparks has gotten consent for, and we are starting to analyze these videos as one piece of the release in the BabyView data set. So we have about 100 hours worth of preschool data that give more visual diversity, more interactions with peers and so forth, to try to go beyond the kind of floor play session that's the meat and potatoes of a lot of developmental psychology. We are using currently Whisper as a transcription engine for this, which actually performs surprisingly well for these fairly challenging videos. And then we can do things like analyzing the linguistic complexity of the input. This is kind of pure developmental psychology in some sense, but it's enabled by this project, and we can see how different activities in the preschool influence the kind of language that kids are hearing. So getting some variation in language across activity contexts. So going back to now some of the questions that we looked at initially with BabyView, or with the SACAM, we can look at pose detection in BabyView. And we were very pleased to see actually that pose detection is both the algorithms have improved, and also the gap between egocentric and third-person video has closed. So in blue there's the COCO validation. In red, that's BabyView. And for the largest pose detection models, this Vision Transformer tuned on pose, we actually do quite well on both data sets. Okay, so basically these high resolution videos really do seem to help. You can kind of see this pose detection thing happening here in another video from Bria's home. So we're getting both kid and adult skeletons pretty well. So it's far from perfect, but it's not bad even when we evaluate on full key points suites. These are also better for object segmentation, not perfect off the shelf, but already substantially better just because of the improved resolution of the camera. Okay, so now we get to actually train models on BabyView and SayCam. This is really very recent data where we train self-supervised vision models and we actually scale up the amount of data that they're getting. So we actually put together SayCam and BabyView Home for about 900 hours, and we're doing pre-training here on 1%, 5%, 10%, up to 100% of the data set with Dino V2, which is a self-supervised objective on a vision transformer. And then we now are evaluating on a variety of downstream tasks, including ImageNet classification, but also depth and semantic segmentation. So really trying to ask, how good are the representations we get from training on kid data? And here we go. So this is for top 1 and top 5 ImageNet performance. And what you see here is the ImageNet baseline at the top, and then the scaling curve that's implied by our BabyView videos. So you really see, I think, pretty shallow scaling here. There's a human performance on top 5 as well. Just to show that it's not our data specifically, this is Ego4D pre-training, which is another half order of magnitude bigger than us, and the scaling is not better. So for this and for depth and semantic segmentation, we really see quite shallow scaling for Dino, at least, for kind of a competitive, contrastive learning algorithm. So this really does, I think, point more towards data gaps. So we're really starting to get a bit closer to what we wanted, which was some kind of evaluation where at least we've got a human top line here, and we've got data scaling, and we're seeing that the algorithms are not scaling in the same way we expect humans to.
Hold on, but ImageNet is very small. ImageNet is like 1 million images.
Yeah, so what you're seeing here is that the diversity and type of those images is producing better image categorization models than what a kid sees.
Or maybe it's just that these models are overfitted to do well on ImageNet. Dino V2 is definitely overfitted to ImageNet. It's really very specific to ImageNet.
Yes, so there are.
Better than you think.
So I think the question is, so the one version of your question is, are there other contrastive learning algorithms out there that would show different scaling performance?
Or rather, maybe don't evaluate on ImageNet.
Okay, well, so that's our transition slide, which is
okay. Sorry.
Okay. So thank you. Yeah. So this was, remember, part 1, which is, hey, let's at least train on what the kids get. Okay, yeah, but we don't. I mean, we at least have a human top line here, but it's not the right task. It's not the right population. So okay, what kind of evaluation would be fairer? So just to say, I don't think it's purely, this isn't a Dino artifact in the sense that we've seen similar scaling in the CV literature from other contrastive learning algorithms. At some point, I'm not an expert on contrastive learning, but the question is, to what extent is this general family of losses incorrect for kind of human representation learning versus is it the specifics of this architecture and this loss? And, you'd probably have at least as informed an opinion on that as I do. Okay, so last piece here, developmental evaluation. So when ChatGPT and GPT-4 were launched, there was this raft of papers that came out trying out various tasks on these models. Some of the tasks that were used were tasks loosely inspired by the developmental psychology literature. I wrote a quite quick paper trying to point out that although these evaluations were inspired by the developmental literature, they weren't inspired by the principles that developmental literature had followed. And in particular, that it was really critical to take some basic experimental design into account from psychology in these evaluations. So developmental psychologists use novel materials to avoid data contamination. So we were constantly talking about Blickets and Gazzers and so forth in order to keep the kids' knowledge from outside of the experiment room in coming into our evaluation. We often use schematic stimuli, not just because they're engaging to kids, but also because they remove correlated cues that might allow for shortcuts around the kind of evaluation of the construct that we're interested in. We often construct closely matched control conditions, which remove some active ingredient in order to get a good sense of what particular component of an evaluation was critical in making it easy or difficult. We seek multiple tasks and measures that converge on the same latent construct. So passing a single evaluation is not enough. You really want a suite of evaluations that are thought to load on the same basic ability. And finally, moving towards a dose-response type of approach in both learning input and in treatment for a particular intervention is critical for revealing some aspects of the mechanism, the way that learning is operating. And I think we've nicely seen that this has become possible thanks to open models where we have checkpoints that are released, and so we can actually look at least training data dose response in some cases. Okay, so these were just some kind of basic ideas that I was playing with, but now we've started to try to put a few of these into operation in actual evaluations. So first, I pointed out that some parts of the gaps that we see might be involved in real basic evaluation differences. And so with Jen Hu, we started to look into these kinds of evaluation differences. In particular, in evaluating kids on some cognitive construct, there's an idea that we often throw around called task demands, which is basically sometimes the evaluation has some auxiliary stuff that you have to do that's unrelated to what you want to evaluate, but makes it harder for the kid. In the case of some kind of text prediction type of scenario, we might, a kind of high demand version of this is to say, hey, tell me what comes next in a prompt. The text is, I take my coffee with cream and then you give the prediction. And so for an LLM, that involves interpreting the question, predicting the token, and then transferring the prediction to the prompt. Whereas an implicit evaluation, where you're just doing next token prediction and the probability evaluation might yield a different type of response. And so this same kind of setup is actually often applied to kids where we say, hey, maybe they just didn't understand the question that you were asking, even if they did have the underlying ability. And there are a variety of documented cases in developmental psych where by making the task question easier, you can see the same thing in much younger children than you would with a harder question. So the idea here is that you might see some developmental curve with lower task demands that is different than what you see with higher task demands. And so you might see a demand gap where if you subtract these two, you see that demand gap narrowing for more competent models. So our idea was maybe some aspect of gaps between kids and adults, or sorry, between kids and models might be due to ways that models are being evaluated as well, with the idea, the intuition being that prompt-based prediction would be especially hard. So we did this in a couple domains. I'll just show you one of them. This is language. We also did reasoning. So this is a word prediction task using the direct prompt versus a meta-linguistic prompt. Those are exactly the prompts I just showed you for 5 model families. And so you see both within and across model families that this gap between the two evaluations narrows the bigger the models are. So for Llama 2, you see quite a small gap. These two tasks are relatively equivalent, but for the smallest models, you actually see quite a large gap. And the same is true for grammaticality judgments. The bigger the model, the less asking for grammaticality information is different than just evaluating a forced choice. So this suggested that details of evaluation do matter here, and that we need to think about how we sync up evals. So we naturally went back and thought, well, how are task demands minimized in evaluation and measurement for kids? And the answer is actually not in unimodal prompts like this, not in language prompts, which actually are quite hard for kids, but in multimodal evaluation. And so that's where we've moved. This is a very new benchmark that we just posted 2 weeks ago, or last week even. So DevBench, which is basically a set of multimodal forced choice tasks. We've got some vocabulary type tasks where it's either 2 or 4 alternative forced choice in response to a word. We've got some kind of compositional sentence interpretation tasks that are used with kids. So this is the test for reception of grammar. So you've got these kind of 4 alternative forced choice, and then actually winnow ground in its simplest condition with adults is very similar. This is basically just trying to get some kind of compositional language interpretation. And then finally, we used a variety of semantic similarity benchmarks, the most canonical of which is like a triad task. Which of these is not like the other? So this is the work of Alvin Tan, who was trying to get together a variety of adult and kid data sets to create this benchmark. I'll just highlight the biggest and most diverse vocabulary benchmark that we added here, which is from a tablet task that we've been working on. So here you go, let's see. This is actually, yet again, Bria's kids, since she's the author of the tablet vocabulary task.
Milkshake.
Is this the milkshake, Mommy?
I don't know. What do you think?
Yeah.
Knee.
Sibling interference here is just for demo purposes. Okay, so the nice thing we can do here is now we can actually compare different ages of child performance to different amounts of training. And this is done with OpenClip, which has all of the checkpoints downloadable. So this is a very nice feature of these open models. And what we're computing is actually model human dissimilarity. So we're not computing performance correlations. Instead, we're actually looking at the response distribution that the kids provide versus the response distribution that the adults provide. A minor detail here, we're not looking also at the peakiness of the response distribution. So we're actually, we're fitting an exponent on the softmax here. So to try to figure out just generally which response options are favored in this distribution rather than just how accurate the model is. And the result here is, this is a ton of kids, by the way. So it's a lot of data, which gives us pretty good estimates, not just of the accuracy, but of the response distribution. And so I think the result is pretty cool, which is that for really the first epoch of training for the models, we actually see that if anything, it matches the 4-year-olds best, and then the older kids less well. But then that quickly flips, and so the later epochs of the model match the adults much better. So kind of suggesting that there is some general correspondence in training to the response distributions. And then if you look at what features of models in general beyond OpenClip lead models to match adults better, you see that across the different tasks, it's actually accuracy that makes them match the adults best. It's not model size, so number of parameters doesn't correlate as well, and it's not amount of training data. It's actually how good the model is at the task corresponds to how good they are at the response distribution. So here's the model accuracy across these different models and across the ages. Again, similarity. And again, you see this interesting now cross-model crossover, which is that the lowest accuracy models are actually matching the 4-year-olds better, but then there's this flip such that the high accuracy models are matching the adults better. So there's this kind of, I think there's some interesting stuff to unpack here in trying to understand the ways that development is and isn't being recapitulated here by overall higher and lower accuracy models, but I think pretty thought-provoking for me. Okay, so like I said, I'm not going to get all the way to connecting the dots here. This is very new, but the basic idea that I've been trying to push is that we should acknowledge that there's really massive, at least prima facie, differences in sample efficiency between human learners and models, and try to get to the bottom of this. One way to do so is by trying to define specific task arenas in which we actually record humans' data and evaluate in a human-compatible way, and then we can really actually get into the details of how big these data gaps are and how general they are across different model classes. So the take-home dogma here is if you want to understand kids, and human learning more generally, you want to train on kid data and evaluate on kid outcomes. Okay, thanks very much.
Hi, this is Dara Yu from Berkeley. So I think you didn't spend a lot of time on it, but towards the beginning you discussed the the fact that like curriculum didn't really seem to have any effect. If anything, maybe it went in sort of the wrong direction. And I'm wondering if maybe you could just speculate as to why you think that might be the case, because in some sense, it seems like that's really like kind of the sanity check, right? Like, we should be able to do arithmetic before we move on to real analysis or whatever. So yeah, maybe I'd be curious to hear your thoughts about maybe the cause of that phenomenon.
So yeah, it's a very good question. There's just a really long history of people trying to figure out when curricularization does and doesn't work for specific learning models. So in kind of neural net draft 1 in the 90s, people were trying to do this, and there were a lot of hypotheses about the ways that children's data might be matched to the limited capacity of their working memory and so forth. People were really wondering about this. And I guess my take on this is that for specific bodies of knowledge, it may be very possible, as you said, mathematics, that curriculum is critical for learning. But for generic representations, I don't how do you represent the distribution in the world of objects? It seems for those distributional representation questions that actually sampling from the distribution that you want to learn is really the right way to, is a better distribution than unless you're kind of So there's learning theory on this that says that under certain circumstances, curriculum learning should work. But my take on it is that hasn't actually, kind of panned out in these cognitive modeling scenarios, at least to my knowledge.
So first of all, let me comment on the curriculum question. I think here again, you guys are overestimating how good we computer scientists are. I think curriculum does not work right now in these models for all the wrong reasons. It doesn't work because there's a stupid IID assumption that's not really reflected in the real world. There is some progress, though. I think tomorrow Joao is going to talk about learning from a single video. So I think it's not your fault, it's our fault. And maybe in general, my overall comment, I think this is just capturing the data is exactly the right direction. I really, really like your work. I think it's don't get depressed by bad performance on ImageNet, because I don't think that's the right metric. I think what you are doing is actually much more cool. In fact, I guess I would ask even more, like pushing it even more into, so with this capturing lots of kids, you're saying, okay, I'm going to do this, lots of mixture of many different kids, just like the ImageNet scenario, knowing a lot of things. But I think a single kid for a long time is maybe even a better evaluation, because if you evaluate it correctly, if you evaluate it like you did with a single kid, then in a sense your training data should also probably come from a single kid. And I think it's actually, it's harder in some cases because you don't have you have very few instances. You don't get to see a category. You only see, one fork, one spoon. But on the other hand, it might force the model to generalize earlier or better.
Yeah, so, okay, just one quick comment on the curriculum piece. I think we're responding specifically to some claims that are out there in the very recent literature suggesting little successes in curriculum learning that we haven't been able to find. So I generally agree with you, and I think your theoretical argument makes absolute sense. I'm looking forward to hearing about how to get around that. On the question of diversity of examples within versus across kids, I think this is fabulous and very tricky to answer from a data perspective, because the amount of data we're going to get from any one kid is going to be, at least one, maybe 2 orders of magnitude less than the full data set. So we're going to hope that, that our superstar family on this graph keeps up the good work, right? But even so, we're probably going to end up with 250 hours from them. And so, yeah, that's going to be an order of magnitude less for that kid. But this is a really critical piece, because it's been a long-standing debate in child language that I think is now largely resolved, whether kids generalize tightly in their early word meanings, whether they think dog just means my dog. And I think the answer to that is basically now resolved to be no. really, actually, from as early as you can measure them, they know that dog means dogs, or at least in a forced choice, they'll choose other dogs over something else. And that's pretty exciting. This is a lot of this work is due to Ellicka Bergelson, but the question goes back to Liz Bates. So to the extent that we have this very narrow data set, we can see some very challenging out of distribution generalization problems in it. And we'll see if we get the data to really pose that in the sharpest way possible.
Hi, okay, yeah. Thanks for the talk. I'm Will Chen from Berkeley. So coming from like a robotics and AI ML side of things, I was wondering if you had any thoughts on sort of going the other way of like what this sort of the insights gained from these experiments could tell about how to like train more sample efficient or whatever models for deployment, since it seemed like the first half of the talk that was sort of the framing that it was going for, and that like there are all these theories as to how children are able to learn so like so quickly with all the like, is it due to interaction? Is it because they're getting so much multimodal data that's correlated and all that stuff? And then like here, when there was sort of like a shift partway through the talk where it's now saying like, oh, when you train on child data, it does in fact match the children better. And as you train on more data, it now matches like adult performance better. Sort of, maybe this is unrelated, but also even from that short video you showed, like that does seem to give some insights towards this question as well, in that like the child was like, oh, like, is this the milkshake? And the mom was like, no, like, what do you, or like, what do you think, right? Sort of, while that is trying to get at just like, how do you access the child's representation, it also does provide like a learning signal in that it's like, oh, like, you should think more about this or something like that, right? So yeah, was wondering if you had any thoughts there.
Yeah, so a lot of our results are in some ways negative. That is, had it turned out otherwise, I would be trying to sell you some model improvement technique. It's got to be that multimodal grounding in the egocentric videos because that's going to make the scale, but it doesn't, right? So it's not just that. So you know, the results I showed you are largely like, don't just go after, you know, at least with current models, don't just go after curricularization, don't just go after this kind of specific data distribution. Now, the rest is speculation. When I talked to Dan Yeamans, my collaborator in a lot of the egocentric work, his speculation is really about the family of losses that are being used here. That these, you know, the kind of, you know, Dino style sort of single image, like let's, you know, crop and rescale and compare and cluster, like that's just not the right loss for the kind of thing that the kid is trying to do. And that argument has been very convincing to me over the years, that the kind of predictive task, whether it's kind of purely visual prediction or visual action prediction, seems like it's probably at least a better family to move to. But that's speculation rather than backed by these data. These data just say some things not to try.
Doris Howe from Berkeley. I was wondering if you've ever thought about like development of animal vision, specifically macaque vision, because I've always been kind of struck by how very limited their visual experience is. You know, monkeys in captivity, they really don't see very much, right? And yet their visual system, you know, is astonishing, and they can recognize so many different objects. And I mean, you know, specifically I study face perception, like they see maybe, you know, 50 faces total their whole life, and then they have this whole machinery that can, you know, distinguish like infinite number of faces. So yeah, just I'm curious about your thoughts about that.
Yeah, I mean, I don't think I can tell you anything you probably don't know unless you disagree. So I'll see if you disagree with the basic presuppositions. So we're talking about loss functions. What I imagine is that, you know, the trick here is, hey, you get a very small and very skewed sample from this distribution, and now find me a loss that projects it into a space such that the projection of lots of other out of sample things are going to be very distinguishable. And that seems like a really interesting learning problem that the primate visual system is solving really, really well for objects and for faces. And it's not being solved by these algorithms. They're much closer to the distribution in ways that are, you know, creating much worse generalization properties. I don't know.
I mean, I guess Jacob Andreas from MIT. Following up on that a little bit, we also make a lot of plots that have number of stimuli on one axis and performance on another axis. And I always get a little uncomfortable doing this comparing to people because you can talk about the sort of number of images or words or whatever that the babies had access to, and then the amount of data that the evolutionary process that put that system into its initial state has had access to. And I guess just how generally, when, in the context of the scientific program, do you think about those two kinds of data, or, all of the, maybe this one macaque has seen 10 faces, but macaque evolution has seen millions and millions of faces?
Oh, I think that's a very interesting result, not an inference from these kinds of plots. I don't feel uncomfortable about it at all, because once you've got that gap, you can ask about. So, maybe I was being a little sloppy here, but this slide here is about bridging some gap that's been measured appropriately for some task with the right data and the right evals. And now we can actually really start to try out these hypotheses, right? And one hypothesis may be a variety of, so the kind of classic, old David Ha work where you do a lot of selection over random networks to try to get some kind of implicit pre-training. That's the kind of thing that somebody interested in proposal A here might be interested in doing. So I feel, I'm not going to say my work is done, but once we've got an actual estimate of that gap, then we can go to work on the cognitive modeling that might provide insight into the nature of that gap. But right now, for me to say 3 to 6 orders of magnitude, that's not very useful if you're trying to use that as a target for. So that's really my focus, is getting that estimate for a particular task and data set and eval really tight. And so then you can go to work on closing it with different hypotheses, which again is just going to be a proof of concept, but at least it's going to give us some theory about how to close it. So that would be the outline of the program.
That's the last question.
Hello. We have an online talk from Melanie Mitchell. She says, at the beginning, you asked what is the explanation for the data gap? Innateness, constructivism, grounding, evaluation. What conclusion, if any, should we draw from your studies?
I'm going to be super conservative and repeat what I said, which is that until we quantify the size, we're not going to get good answers. I'll say that, okay, so again, maybe not my work, but a lot of people thought that when you got multimodal LLMs, you would get some real changes to capacity or to sample efficiency, and that hasn't really happened. So kind of pure image to text grounding has been kind of a big disappointment, I would say, on that. There's a little bit of work by Chung-Shu that, but so yeah, I'm not there yet. I don't have an answer. I'm still defining the terms that we're working on and the size of that measurement. That would be my answer to Melanie.
Great. Thank you for the great talk. Okay, this will be followed by Noah Goodman from Stanford, who's going to tell us about learning to reason.
Well, thanks. Good. Yeah, now that Mike showed you the right way to do science, let me just sort of show you some putzing around. That'll hopefully also be interesting. So maybe 15 or 20 years ago, I started thinking about cognitive science.